object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens.
There's a persistent chill in the scientific community these days as the newly discovered interstellar visitor, 3I Atlas, drifts through our cosmic neighborhood. What began as a fascinating chance encounter has turned into something far more unsettling. The possibility that this object, coming from beyond our solar system and now hurtling inward, could someday collide with Earth's moon. The idea is unsettling in and of itself, and the implications are chilling. It's not just the impact that's worrying, but the cascade of cosmic consequences it could trigger. Before we start, smash the like and subscribe buttons for more updates. Astronomers identified 3I Atlas only recently, yet its trajectory and speed immediately marked it as extraordinary. The fact that it originates from outside our solar system means it did not form from the same protoplanetary disk that gave birth to Earth, the Moon, and their celestial siblings. Its arrival into the inner solar system is remarkable on its own, but what has provoked alarm is the suggestion that its current path might radically intersect the Moon's orbit, leading to a potential high-velocity strike. The sheer number of variables makes this an alarming scenario. A foreign object traveling at an extraordinary velocity, possibly on course to intersect a body as large and gravitationally influential as our Moon. If 3I Atlas were to slam into the Moon, the scale of the event would dwarf common lunar impacts. Imagine a mountain-sized object striking a satellite that humans visit, colonize, and rely upon for both science and future ambitions. The Moon is not a passive participant in the solar system. It exerts tides, stabilizes Earth's axial tilt, and offers a platform for human exploration. A high-energy impact would interfere with all of that. The moment of collision would be pure kinetic energy converted into shockwaves, molten rock, ejecta flung into space, and perhaps long-term destabilization of lunar regolith and orbit. For scientific missions, lunar infrastructure, and the human future in space, the consequences are profound. Because 3I Atlas is an interstellar object, its composition may differ in fundamental ways from standard solar system comets and asteroids. Observations hint at unusual ratios of outgassing, unexpected chemical signatures, and a hyperbolic path that signals it's not bound to the Sun. That means the impact scenario involves not just a conventional asteroid-moon collision, but something whose physical properties, mass, density, structure, might be completely foreign. The speed of the object alone would elevate the danger. An object entering the lunar environment at tens of kilometers per second carries an energy payload that could equal the largest meteor impacts in Earth's geological past. The Moon lacks a thick atmosphere, which means any impact is far more direct than on Earth. There's essentially nothing to slow the object. It would arrive at full velocity, strike the lunar surface, and release practically all its kinetic energy into excavation of the surface, generation of heat, creation of a crater far larger than typical lunar craters, and ejection of debris. Some of that debris could escape the Moon's gravity entirely and travel into space, perhaps intersecting Earth's orbit or even raining down on our planet in the weeks to follow. In other words, the Moon could become a blast site and secondary source of hazard for Earth. Moreover, our lunar operations, current missions, planned bases, satellites orbiting the Moon are all at risk. An object of the size and energy presumed for 3I Atlas could damage lunar orbiters, destroy the near-side infrastructure, and create a field of high-velocity ejecta that poses hazards for many years. The Moon is not simply a passive lunar body. It hosts ambitions of human settlement, scientific labs, and satellite positioning for Earth observation and communications. A catastrophic hit would not just scorch a crater, it could render parts of the Moon unusable for decades. In turn, there are implications for Earth beyond the immediate blow. While the Moon is smaller than Earth and therefore an impact, there doesn't compare to a direct Earth strike. The interconnectedness of the Earth-Moon system means that lunar disruption could translate into Earth effects. For instance, large volumes of lunar dust and ejecta could enter Earth's space environment, increasing the hazard for satellites and spacecraft. Changes in the Moon's orbit or rotation, even subtle ones, could alter tidal patterns on Earth, affecting climate, ocean currents, and coastal systems. The Moon's stabilizing influence on Earth's tilt is one of the reasons life on land developed as it did. Disruption to that system could feed back into Earth's environment in unpredictable ways. Then there's the psychological and political dimension. The discovery of an interstellar object already stretched public imagination of space threats. The idea that this visitor might smash into the moon magnifies fears. Governments and space organizations would be forced to confront scenarios previously relegated to science fiction. Questions of lunar defense, impact mitigation, monitoring of interstellar objects, and international coordination of response would move to the forefront. The moon, once viewed mostly as a target for exploration, would suddenly become a zone needing protection. Human aspirations to establish a long-term presence on the moon could be re-evaluated under the light of this threat. We must consider the scientific opportunity even amid the fear. If 3I Atlas did strike the moon, the resulting crater and exposed geology could offer unprecedented access to interior lunar materials. Scientists could examine ejecta, study shock metamorphism, and learn about both lunar structure and the interstellar object itself via material embedded in the crater's rim. But that opportunity comes with a massive price tag: destruction, hazard, and uncertainty, so it is far preferable to avoid the impact altogether than treat it as a chance for science. One of the more daunting aspects of this threat is the short warning and limited control. The object is already in motion, its velocity so high and path so radical that any attempt to alter it would demand technologies we currently do not possess. The usual planetary defense discussions address near-Earth asteroids, but here the target is the moon, and the intruder is interstellar. Given the object's origin, its behavior may defy the patterns we rely upon, making prediction more difficult. As of now, there are significant uncertainties in its orbit, mass, and structure. That uncertainty itself heightens danger. If the object is larger or denser than estimated, the impact consequences scale dramatically. The potential impact onto the moon also raises issues of timing. If the strike happens while humans are present on the surface, whether via lunar bases or surface expeditions, the risk to life becomes real and immediate. Even if no human presence exists at the moment, future missions could be disrupted. The planning of lunar infrastructure must now incorporate possibilities previously considered remote: high-energy impacts altering the lunar surface, satellites knocked out, dust clouds reducing visibility, and possible debris trajectories intersecting with Earth or lunar orbits. The timing might coincide inconveniently with other space operations, exacerbating logistical complications. Another dimension is the chain reaction across space assets. A major impact on the moon could send fragments into Earth orbit, increasing the hazard for satellites and the International Space Station or future high-orbit platforms. Moon-observing telescopes, lunar telescopes, and lunar orbiters could all be at risk. Space agencies may need to reconsider the resilience of orbiting infrastructure. Furthermore, if debris from the lunar impact reaches Earth, there is a risk of meteor showers or micrometeoroid damage to spacecraft and satellites, echoes of the lunar strike carried to Earth. The moon, in essence, is a keystone in humanity's longer-term plans for space. From building a staging ground for Mars missions to harvesting lunar resources, any serious disruption undermines our pathway to becoming a true multi-planet species. If 3I Atlas strikes, it could force a reset in lunar strategy. Bases delayed, costs increased, engineering challenges multiplied. The psychological toll of a moon strike could redirect investment dramatically toward Earth-based exploration, or even dampen public interest in space expansion for a period. Moreover, the statistical odds of such an event change how we perceive risk in space. If we accept that an interstellar object can strike the moon, previously assumed safe zones must be rethought. Space defense frameworks that focus almost exclusively on Earth impacts may need to expand to cover satellites, the moon, Mars, and other bodies. The scenario shifts from "could an asteroid hit Earth?" to "could a visitor from another star strike any of our assets in space?" It widens the threat landscape, and widening the threat means we must also widen our monitoring, detection, and perhaps even mitigation networks beyond Earth-centric ones. In the cosmic context, such a moment would serve as a harsh reminder of our vulnerability. The moon appears unshakable in the sky, steadfast and familiar, but it is just another celestial body in orbit, subject to the same risks as everything else in space. If 3I Atlas were to slam into it, the moon's constancy would be shattered. For centuries, humans have looked up at it as an unchanging companion. Suddenly, it would become a stage for high-energy cosmic violence. The conceptual shift is profound. Our satellite is not immune. There are also implications for how we interpret the origins and nature of objects like 3I Atlas. If such an object ends up impacting the moon, scientists will gain real-time data on an interstellar body colliding with a defined target. That event could clarify how such objects are structured, how they behave inside solar systems, and how dangerous they might be to any body in their path. It shifts the issue from remote observation to high-stakes planetary defense. The moon striking scenario becomes more than science fiction. It becomes an object lesson in what interstellar travel of random objects might mean for a solar system with human presence. The event also raises deeper philosophical and existential questions. When you capture public imagination with a moon impact scenario, the idea that humanity is shielded by geography or gravity feels false. We often treat space as the final frontier, and ourselves as masters of our immediate domain. An interstellar object smashing into our moon shakes that assumption. It reminds us that the cosmos isn't just a backdrop for human enterprise, but a field of random events in which we inhabit a small vantage point. Our future in space depends on recognizing that we are not immune to cosmic accidents, asteroidal, cometary, or interstellar. Technical readiness is another major point of reflection. If agencies like NASA or other international space agencies are going to confront the threat of interstellar objects impacting the moon or Earth or other assets, then the infrastructure for detection, prediction, and response must evolve. We might need advanced telescopes, space-based sensors, interceptors, or even automated warning systems capable of tracking high-speed intruders whose physics may differ from typical solar system bodies. The existence of 3I Atlas and the potential for a moon strike may fast-forward the urgency of building space defense capabilities beyond the standard near-Earth asteroid campaigns. The question of probability looms large as well. While many experts emphasize that the chance of 3I Atlas striking anything is small, the fact that we're even discussing a possible moon impact shifts that probability from negligible to noteworthy. With the volume of space we occupy and the number of bodies we have in orbit or on surface, even a low probability event becomes high stakes when the consequence is enormous. In risk management terms, the expected value of the impact is massive. It's not the everyday meteoroid hitting the moon, but an interstellar visitor with unfamiliar properties striking a critical body in human space operations. There's also an uncertainty about the physics of the strike itself. An interstellar object may present behaviors atypical of comets and asteroids. Unpredictable outgassing, non-standard density, structural integrity unknown, trajectory potentially altered by forces we do not fully account for. That makes modeling the outcome difficult. Will it break apart before hitting the moon? Will it fragment and cause multiple smaller impacts rather than one large one? Or will it hit intact and deliver full force? Each possibility yields different outcomes for crater size, ejecta patterns, secondary hazards, and the transfer of material into space. The design of mitigation or preparation strategies must account for that wide variation, something far more complicated than standard asteroid impact models. In parallel, the international dimension of this scenario cannot be ignored. The moon is a global asset in many ways, even more of a shared endeavor than many terrestrial resources. If a moon impact by 3I Atlas is in play, then coordination across nations, space agencies, commercial actors, and scientific institutions becomes essential. Who tracks the object? Who issues warnings? What happens if lunar bases are affected? How is the debris hazard managed? These are not questions for a single country. They concern the future of humanity in space. The risk transnationalizes the lunar domain in a way seldom considered in earlier space policy deliberations. The narrative is one of shifting paradigms. The moon is no longer a stable backdrop, but a stage of hazard. The idea of interstellar objects as mere curiosities is replaced by the recognition that they can become active players in the dynamics of planetary defense. The arrival of 3I Atlas, once a scientific marvel, is now also a potential catastrophe in waiting. If it were to collide with the moon, the event would be more than an astronomical story. It would be a turning point in how humanity perceives its place in the cosmos, its vulnerabilities, and the responsibilities of living beyond a single planet. We are living in a moment when human space ambitions, scientific discovery, and cosmic risk converge. The moon, long seen as the next step in human exploration, may now require protection rather than mere visitation. The potential impact of an interstellar object like 3I Atlas raises the stakes in every dimension: science, exploration, defense, policy, future planning. Its journey through our solar system is not simply an observational curiosity. It may be a warning that the cosmos is far less predictable than we like to believe, and our ambitions in space will require not just vision, but vigilance too. The scenario of 3I Atlas colliding with our moon remains a disturbing projection. Yet it offers a compelling lens through which the fragility of our lunar partner becomes magnified. While the detailed trajectory of 3Y Atlas is still under investigation, writing out the full spectrum of consequences helps illustrate how a collision might reshape lunar science, exploration strategy, human space presence plans, and even our broader cosmic relationship. It remains worth emphasizing that 3I Atlas is not a typical asteroid or comet. Observations show that it has an interstellar origin. It is on a hyperbolic path that guarantees it entered the solar system from outside and will leave again. Its composition already shows differences compared with many native solar system comets. For example, an abundant carbon dioxide coma and water ice nucleus. That means the impact scenario isn't simply about rock striking rock or ice hitting lunar regolith. It's about an intruder drawn from a different cosmic environment colliding with a familiar, well-studied body. The unfamiliar origin escalates the unknowns. How will the material behave? How much will vaporize? What unexpected chemical reactions might follow under lunar vacuum conditions? If that collision happens, one of the first major implications lies with the crater and the ejecta blanket. The moon's surface is well mapped and its geology relatively well known. But a sufficiently large and high-velocity impact from 3I Atlas could produce a crater that exceeds typical lunar expectations. The object's velocity, driven by its interstellar inbound trajectory plus solar system acceleration, likely far exceeds typical lunar impact speeds. With more kinetic energy per unit mass, the result is explosive excavation, shockwaves within the lunar crust, melting of rock into molten melt pools, fragmentation of bedrock, a mantle of shattered fragments, and an ejecta cloud that may extend tens or hundreds of kilometers. That blanket of material would radically alter the morphology of the impact region. Pre-existing lunar surface features would disappear or deform, and previously stable regolith zones could be redistributed. The moon's visual appearance, not just locally but perhaps globally via reseeding of dust, could shift. Beyond the immediate crater lies the ejecta risk for the lunar environment and Earth-Moon system. Material expelled at high velocities could escape the moon entirely, entering orbit around Earth or the Sun. Some fragments might fall back to the moon at distant locations. Others could become micrometeoroids sweeping through lunar orbit, posing risk to satellites, orbiters, and human operations. Worse, a significant volume might enter Earth orbit or trajectories that intersect Earth space, raising risk to Earth-orbiting infrastructure. Lunar orbiters, some already in situ or planned, would suddenly face a new debris field hazard. The latency of ejecta effects is prolonged. Years of increased dust and debris hazard might ensue. The moon would not simply be scarred. It would become an active source of hazard. The impact would also have implications for lunar dust and regolith dynamics. The moon's surface has evolved slowly over eons under micrometeoroid bombardment and solar wind exposure. A large impact resets part of that history in an instant. Fine dust would loft across large distances, perhaps even settle in permanently shadowed regions or inside craters previously stable. The redistribution of dust can reduce visibility, hamper solar panels, clog mechanical joints on landers, interfere with optical systems, and degrade habitat performance. If human infrastructure were already established, such dust storms or dust clouds triggered by impact could pose a direct operational hazard. Thermal control systems, habitats, rovers, and instrumentation designed for stable lunar conditions might be forced into redesign or extended downtime. An impact could also pose serious challenges for lunar bases and long-term habitation planning. Assume human presence. The timing could coincide with an active base or habitat. The shock waves could propagate through the lunar crust and surface, triggering secondary seismic events far from the impact site. Lunar quakes, moonquakes might increase in frequency or magnitude, compromising structural integrity of habitats or mining sites. A habitat designed near the impact zone might suffer from vibrations, dust ingestion, or direct structural damage. In designing future lunar infrastructure, contingency for such an extreme event would become imperative. Shielding, emergency evacuation routes, protective domes against melt ejecta, spare systems for dust mitigation, all would rise in priority and costs. From a strategic and operational standpoint, the impact would force a re-evaluation of how safe the lunar environment is. Until now, the moon is often envisioned as a safe way station, a platform for science, resource extraction water ice, regolith processing, staging for Mars missions, and a stepping stone for human expansion. But the possibility of a large interstellar object strike injects a new regime of risk. It might prompt agencies and commercial operators to emphasize resilience, backup habitats, redundant systems, remote monitoring of lunar surface changes, and perhaps even early warning networks for near-moon objects. Insurance models might need to factor in lunar impact risk. Public-private investment in the lunar economy must consider this new hazard profile. We may attempt to protect not just Earth, but our moon as an operating environment. Scientific exploration would feel the impact too, quite literally. Many missions were planned with stable surface conditions in mind. Landers, rovers, drilling rigs into pristine regolith, optical telescopes on the far side, radio observatories shielded from Earth noise. A major impact could disrupt the far side radio quiet zone with ejecta or dust lofted high into lunar orbit, compromising low noise conditions. It might shutter planned far side observatories, delay crewed missions, or require relocations of sensitive facilities. Scientific returns would suffer. Funding might be diverted to mitigation and recovery, rather than new discovery. Even geology and lunar science would shift gears. A fresh, large crater from an interstellar object offers scientists an extraordinary natural laboratory, but only with major caveats. The moon's internal structure could be probed. The impact may expose subsurface layers. Melt pockets and ejecta deposits would open windows into deeper material. But such value comes at the cost of surface commotion and long-term contamination of the local area. The impact could bury historical sites, human artifacts, or scientific installations. It may bury pristine regolith untainted for eons under kilometers of debris, or redeposit material from remote regions. For lunar sample return missions, the context of the surface would be altered. The law of contamination, whereby past surface remains undisturbed for long research continuity, would be broken in the juvenile moment of collision. The Earth's relationship to the moon would also feel a subtle shift. Although the moon is much smaller, and the direct effect on Earth's environment might be limited compared with a direct Earth impact, the interconnectedness remains. For example, if the moon's mass distribution changes, say by removal or displacement of material in a large impact, it might shift its moment of inertia slightly, thereby altering its orbital parameters or rotational state. Given how the moon stabilizes Earth's axial tilt and contributes to tides, any long-term change, even minor, could translate into altered tidal patterns, subtle changes in climate, or even slightly shifted seasons over geologic timeframes. The moon is a stabilizer. Destabilizing it suggests we might have to rethink Earth-Moon system coupling in a paradigm where lunar impacts matter. One can also reflect on how our lunar infrastructure, satellites in lunar orbit, relays, bases, vehicles, may be immediately vulnerable. A large impact event would generate high-speed fragments and dust moving at tens to hundreds of meters per second or more across lunar space. Those fragments could pose burr-like collisions to orbiters, degrade solar panels, penetrate protective shielding, or cause mission failure. It may force a new definition of safe orbit around the moon. Earlier such orbits might have been acceptable, but an impact-derived debris field might require higher altitude, safer inclinations, and avoidance of zones predicted for fallback ejecta. It also raises questions about monitoring of lunar orbit debris and whether we should have a debris tracking network around the moon analogous to Earth's. Moreover, the impact could change how we think about human launch windows and lunar surface operations. Suppose we expected a safe, quiet period for operations. Post-impact, one might anticipate elevated dust, enhanced micrometeoroid flux, and modified local terrain conditions. Rovers traversing previously flat ground might instead face newly fractured terrain, buried boulders, or chaotic ejecta fields. Landing sites chosen for their long-term stability might suddenly be unsafe. This means lunar missions must incorporate worst-case contingency planning for sudden alteration of terrain, and perhaps dynamic relocation of base modules to more stable zones. On the policy and governance side, such a scenario invites international cooperation and perhaps lunar governance frameworks focusing on impact prevention, early detection of incoming space objects, and shared infrastructure resilience. If 3I Atlas or any similar object were to strike the moon, the initiative to monitor interstellar objects would gather urgency. Agencies might form a lunar planetary defense unit, looking not only at Earth impacts but impacts on any human asset or celestial body we depend on. The concept of planetary defense might expand into celestial body defense. The moon, once treated almost as propertyless terrain, would be seen as an asset needing protection. Public perception and cultural implications also run deep. The moon is a symbolic body. Ancient, stable, visible every night, a constant. Imagining it under threat from a cosmic projectile shakes a deep psychological chord. It forces society to confront that even our satellite is not immune to cosmic violence. That, in turn, may affect public support for lunar missions. Enthusiasm might spike in the short term due to existential fascination, but long-term commitment could waver if the moon is perceived as unsafe or unpredictable. Commercial lunar ventures might reassess investor risk, and public space tourism might adjust narratives to include lunar hazard mitigation. The story of space as an unqualified frontier of safety and opportunity might become more nuanced and strained. From an engineering and technology perspective, the scenario demands adaptation. Landing systems, habitats, power systems, and vehicles designed for stable lunar conditions might need redesign. Shielding against high-energy ejecta, autonomous hazard detection systems, dust mitigation technology must become core elements rather than optional. Communications infrastructure might require redundancy if an impact disrupts orbital relays. Navigation systems might need to consider shifting terrain and altered gravitational fields locally. The entire architecture of the lunar economy, from mining to tourism to scientific bases, would need to embed resilience layers previously reserved for rare contingencies. One further nuance is timing. The impact of 3Y Atlas could coincide with other solar system events. The moon often hosts multiple missions at once, sometimes with international and commercial partners overlapping. An impact might disrupt one mission while others are en route, causing cascading mission planning complexity. Launches might be paused, landing sites reevaluated, or resources diverted to emergency monitoring rather than normal operations. The space agencies would need to sequence mission phases with impact alerts in mind, effectively adding a new dimension to mission phasing and risk assessment. The operational calendar of lunar exploration could shift significantly, with windows of risk and required standby modes. Another important implication is background modeling of lunar geologic history. The moon's cratering record is often treated as a static timeline of impacts from distant past. One more significant event changes how we interpret that record. If we were to witness an interstellar object strike the moon, that would necessitate revisions of lunar surface age models, crater count dating that depends on constant impact flux, and even our understanding of regolith evolution. The baseline assumptions for lunar surface age and stability would have to be updated. The moon is not only subject to the typical solar system impactors, but also to rare high-energy intruders from beyond. Lunar science would pivot to incorporate this new category of hazard in our historical models. In a broader sense, the scenario underscores the interconnectedness of exploration, hazard, and infrastructure outside Earth. If the moon can be threatened by an interstellar object, then so too might Mars, asteroids, near-Earth satellites, and space stations. The paradigm you develop for the moon becomes a blueprint for broader off-Earth risk mitigation strategies. A collision by 3I Atlas would thus not just be a moon story, it would become the tipping point of an era in which humanity acknowledges that off-planet is not inherently safer than on Earth. Indeed, in some ways more precarious due to the lack of atmosphere, fewer protective obstacles, and higher sensitivity to disruption. If I shift perspective to future generations, a moon impacted by 3I Atlas might mark an epoch. Pre-impact lunar era versus post-impact lunar era in terms of human habitation. Sites chosen before impact might appear naive in hindsight. New zones of safety might rise. Infrastructure built in the quiet phase would be reassessed, perhaps remodeled or abandoned. Students of lunar colonization would speak of a great lunar impact as a historical boundary event similar to major terrestrial catastrophes. Exploration visions from decades ahead might change. Lunar settlements might be designed deeper, in subsurface bunkers, rather than on open flank. The cost of lunar habitation might rise to incorporate hazard mitigation. Insurance for lunar operations might become standard. On the scientific front once more, One has to consider the chance to study a high-energy interstellar object impact in real time. The moon would serve as a massive natural detector. The shockwave through lunar crust, ejecta altitude, debris dispersion patterns, impact melt volumes, all would offer data unprecedented in human experience. Observatories on Earth and in lunar orbit could capture the event across electromagnetic spectrum. Seismic sensors on the moon, either pre-installed or hurriedly deployed, could pick up the induced quakes, and lunar orbiters could map the evolving ejecta cloud. The impact would yield a bounty of data, but the question remains: at what cost? A major risk to human-led lunar exploration might arise precisely at the moment when science is most eager to deploy. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on NASA's warning about 3I Atlas? Will it really hit the moon? We want to hear from you. Thank you for watching, and see you next time.